I would recommend a liberal arts education to anyone who was like me. It was the perfect schooling for me. I got to take courses that just excited me about everything. I mean, just opened my eyes going away to college.
From the heart of The Ohio State University on the Oval, this is Voices of Excellence from the College of Arts and Sciences, with your host, David Staley. Voices focuses on the innovative work of arts and sciences faculty and staff. With departments as wide-ranging as art, astronomy, chemistry and biochemistry, physics, emergent materials, and mathematics and languages, among many others, the college always has something exciting happening. Join us to find out what's new now.
I'm delighted to welcome today Steve MacEachern, Distinguished Arts and Sciences Professor of Statistics at The Ohio State University. His research interests focus on the development of statistical models and methods to fit them, evaluation of the adequacy and deficiencies of models, and investigation of novel methods of inference. Dr. MacEachern, welcome to Voices.
Oh, thank you, David. It's a pleasure to be here.
I want to start there. As I was prepping this interview, I thought, does he study statistics about something, or does he study statistics? The field, the way to do statistics. Is that an apt description of your research interest?
It is. It's funny, in the world of statistics, there are people who say, I'm going to study statistics on agriculture.
Right.
And they do brilliant work on agriculture. And somebody else says, I'm statistics and material science. And that's their focus. And they get into the field, they learn so much about it. And then they also bring their statistical training to bear to really do things that people who might be a pure ag person could not do, or pure material scientists could not do. For me, I'm just interested in different things, I think by nature. And what I want to do is find out what strategies, what methods work, cutting across one discipline to the next to the next. And so what I do is look at course-specific problems, but I'm looking for the pattern which holds up across many different problems, ideally in many different areas. And that's what I think of as really statistical methodology, the statistics, as you say so well.
I don't know how it is in your field. In my field, someone who studies the discipline or studies the method, there tend to be few of us. Is it true in statistics as well?
It's a real mix in statistics. And so if I think about things, there might be 2/3 who study specific things and 1/3 who study just methodology in general. So a big mix. And of course, in our department here at The Ohio State University, we have a wonderful mix of people, very different interests, very different backgrounds. And when we all come together, the interchange of ideas is just phenomenal.
Was your PhD in this sort of area, or how did you come to this particular interest in statistics?
It has to do with my PhD and my training. I went to the University of Minnesota. At the time, I had remarkably broad training in statistics. We got hardcore stat theory that's essentially mathematics, theorems and proofs. There were people who were doing very, very applied work, essentially building modern applied statistics, where computation was not the same in the late 1980s as it is nowadays. But they were ahead of the time and really looking to the future and saying, if we had a little better computing, what could we do? Developing the methods that now are routinely used. There were other aspects too, a lot of computing at Minnesota at the time, and one of the very, very few places where you could get good training in Bayesian methods, which is kind of a subfield of statistical methodology.
Is there any difference between statistics and what we're today calling data analytics? I'll state it as baldly as that.
Yeah, that's one where there's a lot of conversation within the field of statistics and more broadly across universities. I think there are differences. Whether you call it data analytics or data science is a term that I'm a little more comfortable with. Statistics is really about writing down models that capture the production process of data and then using those models to make predictions, to understand the world, and so on. Something that is implicitly a part of data science or data analytics, a bigger part of it than it is of statistics, is working with data itself. Massive databases. You have to figure out how to capture that data, how to wrangle it. And quite frankly, there are other communities that are better at that than people in statistics. When I look at it and think of data science, I think that a lot of the data part of things comes from computer science or particular fields where the data is collected. You're a historian. Tons of historical data. But how do you get it? How do you digitize it? Put it in a form where you can bring some of the modern tools to bear on it. That's a huge endeavor, and that's not traditionally been the territory of statistics. We're much more about building the models. I would say putting the science into data science.
That was my next question. What distinction are you drawing between data science and data analytics? Why do you prefer saying data science?
Data analytics, to me, always has a feeling of data and statistics used for business purposes. And I'm not sure it's right that it has that feeling for me, but it just always conveys that sense to me. Data science, I think, puts a little more emphasis on kind of the hard-edged techniques that I think are absolutely crucial to the field.
A moment ago, you mentioned you do work in Bayesian methods. First of all, what do we mean by Bayesian? And tell us a little bit more about the work you're doing here.
Yeah. Bayesian methods are a particular kind of statistics. And the defining feature of Bayesian methods is really the use of probability to describe all of our uncertainty about the world. And so the best language ever developed to describe uncertainty is the language of probability. I might say, what's the chance that it rains this afternoon? 30%. We implicitly, internally know what that means. But if we'd like to describe complex situations and potential events, how do we describe what might happen in the future? The language of probability again. Now, it seems odd that you could use that same language to describe things that are not random at all, right? We might try to describe the height of you or the height of me. And of course, I don't know exactly how tall you are, but I could capture my uncertainty by means of a probability distribution. And that probability distribution will not, we're going to draw your height at random from it, does convey my uncertainty. So for Bayesian methods, we start by describing our uncertainty about the world in terms of a probability distribution. We go out, we do experimental work, we have observational data, we bring the data to bear on our beliefs, we call them prior beliefs, and we say, what do we believe after we've incorporated the information in the data? And that we call our posterior distribution. The notion is we always work with probability. Prior distribution is a probability distribution. We have models that involve randomness, probability is implicit in those, and we get to the posterior distribution. We still have uncertainty about the world, but we describe it in terms of the language of probability. And then we use that to make forecasts, to make decisions, make predictions, anything you want to do.
I hope this doesn't come across as glib. So how is probability determined? Is it essentially an educated guess?
Ooh, there's one that people have argued about for decades, if not hundreds of years.
And maybe I wasn't glib.
No. So there are different ways, and of course that depends very much on what you're doing, right? If I sit down and there's something I know virtually nothing about, I could take a guess, which might not be particularly educated, and that could describe my beliefs or uncertainty about the world. If we think about many things at universities, people study them. They devote their career to studying perhaps fossils. They might devote their career to studying language and how a language changes through time. In those cases, there's already an enormous scientific literature. And so where do probabilities come from? You go to the literature, you find out what people know, and there is a little bit of translation of all that literature into a probability distribution, but it's a modest translation. The best probability models are ones that are informed by data, and for that you have to look, you have to find the data and use it. That's actually part of why Bayesian methods have become so popular. Now there's data everywhere you look, and with that we can really build very, very good prior distributions where we say we've got our beliefs about the world, let's increment it, add a little bit more data to a particular time and place, and now we can say what do we believe about this time and place. Very effective techniques.
You gave the example, for instance, what's the probability of raining this afternoon? Do we have data about that future?
Oh my goodness, yes. There's an amazing amount of historical data on the weather, right? And not only weather, but climate, large-scale changes through time. If you turn into the morning news, very often I'll see 2 or 3 different models that are used to produce forecasts. In fact, the weather people, Channel 6, they'll talk about the difference between the 2 weather forecasts and say one model produces this forecast, another produces this forecast. One says 30% rain, the other says 50% rain. Well, you're in the right ballpark, 30 to 50%.
How can there be two different models?
That's a good question. People have different modeling philosophies, and some are very, very empirically driven. Essentially, we've got a lot of data. Let's look at it through time. And what we're going to do is just say, what fraction of similar days did it rain, and turn that into a probability. Others are going to rely a little more heavily on weather patterns. The air currents kind of swoop down west to east generally in the United States. And they see, is it raining in Chicago today? Might be raining in Columbus tomorrow. And they give a little bit more weight to those weather models and flow of things in the atmosphere. So different people are going to look at the same data and very legitimately come to a little bit different conclusion about what the future will hold.
You work in Bayesian methods. What have been some of your research areas here in Bayesian methods?
I'm probably best known for my work on non-parametric Bayesian methods. And that's a mouthful. So first off, it starts with this notion of Bayesian methods. We try to use probability to capture all of our uncertainties. The non-parametric part means that we don't want to pin ourselves down too strongly. We've all heard of the bell curve or the normal distribution or the Gaussian distribution, different names all over the place. But that really says that you got a lot of data in the middle and it goes down symmetrically on both sides. The truth is, when you look at a lot of data sets, they simply don't follow that pattern. One of the realizations I had years ago was right before my daughter was born, my first child. And if you look at the birth weights of babies, they do not follow normal distribution. There are some very, very small babies who are born, and there are a few big babies, but not very many. And there is no baby that's 20 pounds, right? It's just not going to happen. And so you look at it and you have a distribution we would describe as left skewed, kind of a long left tail for those low birth weights trailing off. If you look at adults in the United States, it is not a left tail distribution. For weight, it's a right tail distribution. We have a few people who are very, very big, and we have other people that are maybe small, thin, but nobody is truly emaciated in the same way that small babies are small. So you could turn to a distribution that has a long right tail, skewed to the right. And the question is, if you thought about weight through time, through someone's age, the population level distribution changes from a long left tail to adulthood, a long right tail. And of course, it's got to be continuous. There's no magic change where when you turn 13, all of a sudden the weight distribution changes. It evolves and moves continuously through time. So the question is, how do you write down models that capture this notion where you have one distribution which is not a symmetric bell-shaped curve at one point in time? Another point in time, you have a different distribution, not symmetric bell-shaped curve, but it looks different. The shape of the data is different, and you'd like to build continuity in as well. Non-parametric Bayesian techniques allow us to do that, and it's just sort of remarkable that you can do it, but the techniques let us do it, and they've opened up all sorts of modeling opportunities where it comes back to the methodological question. When you look for this pattern and you've seen it once, you see it again and again and again. And then you can look at the numbers more carefully, and the pattern is real. It's not an accident. It really is a genuine pattern, a real pattern. Economics. You can think about the income distribution. And incomes, of course, do not follow a bell curve. There are a few people unbelievably wealthy, many, many more people who are struggling to make ends meet. And when you look at that, you can take a snapshot at one point in time. You have a distribution, not a normal distribution or any other distribution you'd put a name to. And then you look at it and you can say, how does this distribution change through time? And it's clear that there have been changes through time in the United States and in other countries as well. You'd like to be able to track that and really work with these distributions that are quite flexible and yet do have properties of continuity built into them.
Does that mean that the bell curve is more exception than rule?
I think yes. I would say it's more exceptional than the rule. And yet, certainly there are some things that follow a bell curve quite well. But we should always be on the lookout for things that are not quite following the bell curve. And for our statistical techniques, we need to be aware of departures from the bell curve and need to have techniques that are robust. They're not destroyed by something not quite following a bell curve.
You just used the word robust.
I did.
You just anticipated my next question. You study robustness in statistical models. What does that mean for a model to be robust?
Robust is, the word of course is an English word forever, and the statistical use of it did come from the general use of the word, and yet it has technical meanings in the world of statistics. By robust, we generally mean two things. One thing is that if you were to take a little bit of your data and just change the values, if we're thinking about heights that do follow a bell-shaped curve quite well for adults of one gender or the other. If you think about heights and you said, let's take a few tall people and we'll just make their heights taller, or we'll misrecord their data and write down numbers that are simply not accurate but too tall, you could ask what happens. And if you're computing the average height, just the sample average, when you make those tall heights even taller, you pull the average up, you change it. That's not very robust because you're sensitive to a small number of data points that might have extreme values. On the other hand, if you computed a robust summary, something like the median, the 50th percentile, if you take a tall height and you make it even taller, the median does not change at all. It's still what's the typical person's height. So that would be one example of the use of robustness. Of course, we're interested in it in a much more subtle fashion in statistics. It's a big issue now with AI techniques, by the way, in that you can imagine that in a competitive landscape, companies might want to pollute a little bit of data so that other people who grab that data and just use it naively are tricked and are not going to do very well in our competitive landscape.
What makes a model robust or not robust? What are the factors? Is it the number, the n in the set? Or?
It's not really the n, although if n is 1 or 2, it's not terribly
n
robust.
N meaning number,
right?
I should explain.
But if you have a sizable data set, it's really the pattern of the observations. But it's also what you're going to do with those numbers. And so there we're back to the statistical methodology, how you treat the numbers. And in general, what we want to do is give very unusual observations relatively little weight in our final inference or our final summary. And I say that, but I have to say it with caution, because there's always this question, right? If Bill Gates is in the data set, he really does have a big salary. He is a rich guy, right? And so there's always judgment involved, even when you're looking at masses of data and large amounts of data. What's the real pattern? What's an artifact, which is just due to misrecording, due to misinterpretation of the data, due to gluing different databases together, where afterwards you look at it and say, maybe we should not have glued those two databases together. They're fundamentally representing different phenomena.
How do you work it with robustness? Are you writing theoretical papers or are you critiquing working models?
It's a real mixed. And so anytime we look at statistics, we do want to write down mathematical theorems and prove them and say, if we make these particular assumptions, then what we have are our conclusions. And it's airtight. I mean, there's no doubt about it. It's simply mathematical truth. That's a gap, because reality, well, we've made assumptions, and those assumptions are never quite right. And different people will describe things differently. A lot of people will say, well, the assumptions are a good reflection of reality, so I'm happy to make them. I turn that around, and really I say, we can do the mathematics, we make the assumptions, we prove the theorems. And the question is reality close enough to those assumptions we made, where we expect the pattern in our theoretical work to hold up in practice? It's a good question. There's always judgment involved. But what we really have seen when we try the techniques out on real data sets and problems that people care about, most of them work pretty well. And when they don't work well, then we start an investigation. We say, okay, why did it break? What went wrong? Which assumption that we made is just too far from reality? Is there a way we can create a better assumption that's closer to reality, and then redo the whole process, create better methodology, in fact?
You have said elsewhere that modern statistics is often more about prediction than explanation. What do you mean by this?
Well, what I mean is that the scope of statistics, I mean, it's embedded in everything that we do nowadays. And so imagine that you had an online shopping platform, a place like Amazon, a place like Etsy, could be a bidding platform like eBay. They're not necessarily terribly interested in what happens within my mind when I'm making a purchase, but they do know whether I'm going to buy the item or not. They want to know what price point I will bite on so that they can price their items accordingly, still sell them to me, and move their inventory through. That's a prediction problem. They're trying to predict what I as an individual consumer will purchase. But of course they're interested not only in me, they're interested in millions of customers or potential customers. So we think of that as a prediction problem rather than a problem that's really what's the scientific understanding of a theory in physics or chemistry or sociology, political science. There are a lot of other problems that are prediction problems, but we don't naturally think of them that way. Do a search on Google. You'll get that first page of results, top to bottom. And of course, what they're trying to do is give you a feed, which is a good feed, things that are of interest to you, things that you might click on. And they're very interested in what are you going to click on. And that, of course, is tied eventually to things like ad revenue for people who are going to purchase ads. Which ads? Well, there's a question of somebody who does this search, what are they interested in? And can we actually adjust search results to give them what they're interested in, but also in a way that's going to make a company like Google money.
When you say that statistics is more often about prediction than explanation, are you just stating a fact or are you making a value judgment?
I think that one is a value judgment.
Then you'll have to explain what's your judgment here.
Different people in the field bump into different parts of statistics. So if you were to talk to someone else, they might say, oh, no, statistics is much more about the understanding. We do write down the models to try to understand the phenomenon. There is absolutely no doubt about that. A lot of science is trying to understand phenomena. And yet, it goes back to, I guess, my days as an undergraduate, which is a long time ago. I went to an absolutely wonderful school, a small liberal arts school in southern Minnesota. And there I learned that for many disciplines, you're not looking for an explanation that captures everything about your subject. So it really hit home when I was taking a course in anthropology of all places. And they talked about different cultures and worldviews in different cultures. And there was no way that a kid from Minneapolis who went to college 50 miles away in southern Minnesota could really understand what it is like to grow up in a very, very different culture, a completely different culture, different part of the world, different time. Simply not going to happen, right? And yet, by studying different theories in anthropology, I might get a glimpse into that culture and a glimpse into what life would be like as a different person. And of course, when you do that, you're happy to have several different theories, none of which explains everything, but each of which is productive because it gives you a different look at the world. And perhaps not searching for a single theory that gives the ultimate understanding of everything. I'm not sure that can ever happen with people. And yet we are very interested in understanding more. And so the theories and the understanding absolutely is important. It's crucial. And yet it's not only that. We are interested in making concrete predictions as well.
You just drew attention to this, and I wanted to ask you, you make a very interesting distinction between data from the hard sciences and data from, say, the social sciences or data about people. What are the differences here?
When I think about the hard sciences, I'm thinking about something like physics or chemistry, astronomy, places like that. That, OSU has wonderful, wonderful groups of people who live in those spaces, engineering very much in that same space. There simply is a truth about the world. In those disciplines, it's a quest to find out that truth. When we think about data that come from the hard sciences, a lot of it is tied to the physical world. As far as I can tell, a proton is a proton is a proton, and it doesn't matter a whole lot where you are or when you are, it's still a proton. That's what lets you look for underlying truths, physical laws, which are really going to be the same no matter where you are. When you do that, you can often do experiments that are very tightly controlled. Wonderful idea of what you're trying to do, how you're going to measure that. And you tend to get very, very high quality data. If an experiment goes bad, it's usually very easy to see that the experiment went bad. It's just a collapse of the whole process, and you can easily identify it. Data in the social sciences, data in the humanities as well. quite different because it's about people. And it is true that a person is a person is a person. We're all people, right? And yet individual people behave completely differently. And it's not a bad thing. That's part of the joy of living in the world and interacting with people. People are individuals. They're unique. And with that, although we can hope to pick out patterns that generally hold up, to say that that pattern always holds every single time across space, across time, across different cultures, across different languages, it's hard to believe that there's a universal truth that is the same kind of universal truth that we get in the hard sciences. To me, of course, that means that the social sciences are far more interesting because they're about people, but that's my bent.
So you just mentioned you went to a small liberal arts college. Did you know when you went to college that you were going to be a statistician? Did you know when you were 5 years old you were going to be a statistician? Or was there another path that you were going to follow?
I had no idea when I went to college what I was going to end up doing. And so when I started as a freshman, I thought maybe a math major, because I loved math, was always good at it. The beauty of mathematics, the purity of it, it just really excited me, turned me on. But also I loved history. I was torn between math major or history major. I took a few courses and I thought, boy, these math courses, they just have grabbed me. So I went the direction of a math major. Oh my goodness. I would recommend a liberal arts education to anyone who was like me. It was the perfect schooling for me. I got to take courses that just excited me about everything. I mean, just opened my eyes going away to college. I eventually ended up as a math major, and that eventually cascaded into graduate school in statistics and my position here at Ohio State and my life. But, oh my God, I still love everything else. I try to grab books and read and learn a little bit about the world.
Why statistics for graduate school and not mathematics?
Ooh, it's interesting. There was an internship I went on between my junior and senior years of college. I'd known about statistics since I was a little kid. My dad actually taught statistics in College of Education at University of Minnesota. The internship, I spent 4 days a week working in an insurance company, 1 day a week just learning mathematics. It was sort of funded by the National Science Foundation. Really fun, really interesting. I loved the work as an actuary sort of in training. And I thought this would be great for 2 years or 3 years. I was learning new stuff. It was interesting. It was fun. I got to do technical work that I loved. And then I thought to myself, at some point, the novelty is going to stop. Because I could see people who'd worked there 20, 30 years, very good at their jobs, wonderful jobs. They love their jobs. And yet, for me, I need novelty. I have to have a flow of new ideas. It's just constant and continual. And I was not going to get that working in that kind of job in a corporate world. At least I didn't think I would. So it sort of convinced me, I'm going to try graduate school out. I knew that in graduate school, you could go to school, you could work as a teaching assistant, they would pay your tuition and give you enough money to live on. The chance to go to school and not pay anything was wonderful. Why not pure math? I love the pure math, and yet for pure mathematics, it's very specialized if you're going to be a researcher in pure math. And I could see that for me, I would be immersed in a narrow area, and I would work on a dissertation on that and continue to work on that in research. And at some point, the novelty would wear out. Mm-hmm. Statistics was something I can change every 2 or 3 years if I want. My actual pace is changing maybe every 5 years or so. But I can say, boy, I want to look at something, get into it, start reading papers, talk to people, build a few connections, and be working on something completely different a few years from now. And that kind of flow of novelty gives me an energy that I love.
You earlier said you've been at this a while.
Indeed.
What's one thing that you wish the general public understood about statistics?
That one is hard to say because I'm not always sure what the general public's perception of statistics is.
Fair enough.
But what I would say is statistics is really about using data and using our understanding of the world that we capture in statistical models productively to make decisions and ideally to make the world a better place. It's hidden in a lot of things where you never see it, but it is present, and it's a wonderful discipline. If you're young kids, think about being a statistics major. It'll be a great path in the future. If your parents send your kids to be a statistics major.
What are you working on now? What's next for your research?
Oh, what's next for me? It's going to sound trite, but AI is changing the world. In the field of statistics, in fact, in many fields, technological changes drive changes within fields. Mm-hmm. And we saw it long ago in the world of statistics. We moved from mainframe computers and punch cards, if you're really old, you've heard of those, to personal computers sitting on a desktop. And of course, the early ones have no power compared to what you have in your phone nowadays. But that change let us do statistics in a different fashion. Technological change produced change. Other changes have come about as well, some of which I've witnessed, which is really fun. But AI is really remarkable, and there are enormous changes that are hitting the field of statistics as well. One of the classic questions that people often ask is there any need for statistics in the future? And it's driven by people seeing the success of things that are called AI. Something which is true. A lot of statistics is embedded in what we think of as AI. Mm-hmm. So it is actually a part of the driver. It's not something new and distinct and separate. It's tied very closely to statistics. But statistical techniques let us pick out big, strong signals where you have a few explanatory variables or predictor variables, things you've measured on, say, people or the physical world. And those, if they have a strong signal, are very easy to capture with traditional statistical tools. Now what we see is enormous databases that contain a few really good predictors and a lot of stuff which is very tangentially related to whatever it is that you're trying to study or forecast or predict. And so a big task is, how do you sort through that massive data to find the strong signals? Also, how do you create signals out of the massive data where there are some very, very weak signals that cut across many different predictors? You have to have ways of aggregating that or summarizing it to create effective predictions. And that's part of what I really am excited about now, trying to study. And of course, you go to our department, it's full of people who are engaged in studying this.
Steve MacEachern, thank you.
Oh, thank you, David. It's been a pleasure.
Voices of Excellence is produced and recorded at The Ohio State University College of Arts and Sciences Marketing and Communications Studio. More information about the podcast and our guests can be found at go.osu.edu/voices. Voices of Excellence is produced by Doug Dangler. I'm Jen Farmer.